Let's continue now. We have so far looked at field extensions, algebraic field extensions, transcendental field extensions, degree of an algebraic element, degree of an extension of fields, and we also looked at how to add roots of a polynomial, and we learned about splitting fields. So now we come to the final topic of the course, which is finite fields. So finite fields are fields which simply are finite sets. So these are fields containing only finitely many elements. Okay, so in this part of the course, which is the final topic, we are going to study this and we will prove a structure theorem for finite fields. So what are some examples of finite fields that we know? So for example, we know that Z mod 2Z is a finite field containing two elements, Z mod 3Z, Z mod 5Z, Z mod 7Z, and so on, right? So these are clearly fields because 2Z, 3Z, 5Z, 7Z are maximal ideals of the ring of integers. So when you quotient by them, you get a field. And as you observe, the order in each case here is a prime number. In fact, you do not get a field if you take Z mod 4Z. Okay. Similarly, you do not get a field if you take Z mod 6Z and so on. So these are the orders. So orders of order, remember, means number of elements. So remember from group theory, so I am going to use that terminology. Now that we are talking about finite fields, the number of elements is a finite number, so we call that order. So the first question I want to address is, what are possible orders of finite fields? So I want to eventually prove a theorem which completely classifies finite fields and tells us a lot about their structure. But in order to motivate that theorem, I want to quickly discuss some examples and some initial observations. What are possible finite orders? So clearly, for every prime P, remember prime number, when I say prime in this context, it's a prime integer. There exists a field of finite field, of course, of order P. So simply take and we will prove as part of the structure theorem that this is the only such field up to isomorphism. So we can usually, because of that, we denote this by FP, F written in this bold fashion. So FP stands for the finite field of order P. So certainly for every prime we have that. On the other hand, I will prove a small lemma here, which says that if F is a finite field, then the order of F is P power R, so Q, which is P power R for some prime P and a positive integer R. P is of course prime integer. So the lemma says that if F is a finite field, then its order is a power of a prime number. It cannot be any other order of a field, can't be any other number. So for example, there can be no field of order 6 because 6 is not a power of a single prime number. So I will write that after proving this. This is one of the most standard things that you learn when you start talking about finite fields. What is a possible order of a finite order? It must be power of a single prime number. So the proof is very simple. Consider the unique ring homomorphism from Z to F. Remember, earlier in the ring theory part of the course, we showed that for every ring R, there is a unique ring homomorphism from Z to R sending 1 to 1. So F being a finite field is also a ring, so there is a unique ring homomorphism like this. So immediately we observe that phi cannot be injective. Since f is finite, phi is not injective. Why not? If phi is injective, z sits inside f, right? Is the language we use. But z is infinite, so then f would also be infinite. So if f is finite, phi cannot be injective. Hence, kernel of phi is not 0, right? Not injective means kernel is non-zero. Since kernel of phi is a prime, so note that I will say that we know z mod kernel phi is isomorphic to a subring of f. So is isomorphic to a subring of f. That is the first isomorphism theorem, right? So namely the image of f, image of phi. So we have an isomorphism from z mod kernel phi to image phi, which is of course a subring of f. So f is a field. Any subring of f is an integral domain. So z mod kernel phi is an integral domain. Hence kernel phi is a prime ideal. And it is non-zero because capital F is finite. So kernel phi, remember all ideals in Z are multiples of a particular integer n. Prime ideals are either the zero ideal or prime number multiples. Because kernel phi is not zero, it is of the form pz for some prime p. So the upshot of all this is, so f is a field extension of z mod pz, right? Z mod kernel phi is z mod pz is an injective, it sits inside f. Now this is a field, this is a field. And what do we call such a situation where we have a field contained in another field? That is what we call a field extension. So f is a field extension of z mod pz. Suppose r equals the degree of this field extension. Because f is a finite field, the degree of the field extension cannot be infinite, right? This is simply the dimension of f as a z mod pz module, z mod pz vector space. It certainly cannot be infinite because f itself is finite. So there is certainly a basis containing finitely many elements. So this is finite. Now this is a simple counting formula. Counting argument shows that the number of elements of f is p power r as claimed. And the reason, so this I will not do in detail because this is something that you would have seen, similar arguments you would have seen in other courses. This is because r is the degree of the extension, right? So I will give a sketch of the argument, not the full argument. So let's say v1, let me use alpha 1, alpha 2, alpha r in f be a basis of f over z mod pz. Okay, if this happens, then every element of f can be written uniquely as a linear combination a1 alpha 1, a2 alpha 2, ar alpha r, right? And where are ai's? Ai's are in z mod pz. Now this is where the counting comes in. So essentially the choices come from how many choices we have for a1. So these are r choices, sorry, p choices, right? Because a1 can be any of the p elements of z mod pz. Similarly, you have p choices here. Similarly, you have p choices here. So totally p times p times p r times, so p power r choices. So the important thing to notice is that each different choice gives a different element. That is a consequence of the fact that alpha i's are a basis, and no two choices can give the same, in other words, no two choices can give the same element because they are linearly independent. Every element of f can be written like that because they span. So that means there are exactly p power r choices. That means the number of elements of f is p power r. So the order of f is p power r. Okay. So now this we have proved this theorem that finite fields can have order. Sorry, I want to insert a page here. So finite fields can have only order p power r. So corollary. So I am doing this because I have written the next theorem already. So corollary is, as a simple example, there is no field of order 6, right? There is no field of order 6. There is no field of order 8. Sorry, order 8 is not a problem, but 10, 12 and so on, right? But still this leaves the question. The proposition that I proved earlier says that if a finite field exists, its order cannot be only of the form p power r. But the converse, is it true? Is there a field of order p power r for every prime p and every positive integer, or at least one? So this is the question that we want to address in this video when we talk about the structure theorem for finite fields. So as a first attempt, so the answer is going to be yes, and much more in fact is true, but as a first attempt we will observe the following. Let's look at q equal to 2 squared, which is 4. This is not prohibited, right? From the lemma, we do not know if there is a field like this or not. It is not excluded by the lemma. So is there a field of order 4? So what do we do is, certainly we cannot take z mod 4z because z mod 4z is not a field. We cannot take z mod pz for any prime because z mod pz has order p. So and 4 is not prime. So we have to do something new, right? We cannot use the existing collection of finite fields. So what do we do? So just the notation here, I have already mentioned this before. The notation is, I will use fp to denote z mod pz. And more generally, I use f sub q to denote a field of order q. So for prime numbers, we know they exist, so I have introduced it. We will also prove as part of the structure theorem that any two finite fields of the same order are isomorphic, so that justifies using the single notation for such fields. Okay, so let's take 4. How do we construct a field like this? We know a method to construct new fields, right? We can take a field and consider its extension fields by killing irreducible polynomials. So let's start with z mod 2z. So I will call it f2. So if there is an extension field k of f2 of degree 2, then k will have 4 elements, right? So if k is a degree 2 extension of f2, then order of k, which I will denote by this symbol, will be 4 by the counting argument that I gave in the previous slide. Okay, because there is a basis of 2 elements, coefficient of each basis can be any of the 2 elements of f2, so there will be 2 times 2 many elements. Now the question is, how do we construct a degree 2 extension? All we need to do is find an irreducible polynomial in f2x of order 2 of degree 2 and take, so irreducible polynomial, let's say f, an irreducible polynomial f in f2x of degree 2 and take k to be f2x mod f, right? That's all we need to do. Because of everything that we have done so far, f2x is a polynomial ring in one variable or a field, and as such it is a principal ideal domain. And if you take an irreducible polynomial, the ideal generated by that is a maximal ideal. So when you go modulo that ideal, you get a field, call it k. So first of all, k is a field. Moreover, because it is generated by x bar over capital F2 and small f has degree 2, k colon F2 will be degree 2. This is something we have shown. The degree of an element is equal to the degree of the extension. So then k is the desired field of order. So all we need to do is find such an irreducible polynomial of degree 2. So now how do we, if you do that, we have our field of order 2. How do we select such a thing? So simply take f equals x squared plus x plus 1 in f2x. So I claim that this is irreducible. How do we show that? This is irreducible. This is very easy. Why is that? See, if a degree 2 polynomial, verifying that it's irreducible or not is very easy. All we need to check is that it has no roots, because if it splits, it is not irreducible. That means it is reducible, and it splits. Then, because it's degree 2, factors have to be linear, and a linear factor corresponds to a root. So, does it have a root or not? There are only two elements, right? F2 has two elements. We call them 0 and 1. So, f of 0 is 1, which is not 0, and f of 1 is 1 plus 1 plus 1. What is 1 plus 1 plus 1 in F2? That's also 1, right? Because that's 3, which is 1. So f has no root, so it's irreducible. So take k to be f2x mod f, and it's supposed to have 4 elements. I'm going to list the 4 elements like this. So we have 0 and 1. Remember, it is going to contain f2. It is going to contain f2. The other elements will be alpha. Remember, x squared plus x plus 1 is declared to be 0. So you take x bar to be alpha. The notation is you call alpha equal to x bar. Then you will have x bar plus 1, and that's all. Remember, 0 comma 1 comma alpha is a basis, and these are all the elements. If you take alpha squared, that's already alpha plus 1. So what I am saying is that alpha squared is alpha plus 1. What is alpha cubed? That's alpha plus 1. So you can write it like this: alpha squared times alpha. So that's alpha plus 1 times alpha. That's alpha squared plus alpha. And what is alpha squared? Alpha squared is alpha plus 1. So this is alpha plus 1 plus alpha. This is 2 alpha plus 1. What is 2 alpha in this field? 2 alpha is actually 0. Right? So 2 is 0 in F2. That is the crucial point, and hence also 2 equal to 0 in K. It's an characteristic 2 field. Characteristic is the term we use for the generator of the kernel of the unique ring map from Z to F2. In F2's case, it is 2. So that means 2 is 0. So this becomes 1. So all powers of alpha are also here. Similarly, you can check that all powers of alpha plus 1 are also here. So what we know is that K cross, which is the non-zero elements of K, is actually a cyclic group of order 3. K is a field of order 4. K cross is a field of order, so this is Q and this is Q minus 1. Okay, so I am trying to do in this example the structure theorem that I will now state, so that you see what the theorem says in general. And this is a very simple example, but it is in fact illustrative to do this. Okay, so now I have already written this. Let me show to you the statement of structure theorem of finite field. So this is, I will call this structure theorem for finite fields. So it nicely groups together all the statements that we can prove about finite fields, and together they tell us a lot about finite fields. Finite fields are well understood. Unlike extensions of Q, where there is infinitely many elements and there's many things to study, finite fields are sort of completely understood from this theorem. So I've already written this to save the time. So let me just read through this. If P is a prime number and Q is any power of P, the first statement is the answer of the question that we stated earlier. Does there exist an element of order P power R for every P and R? And the answer is yes. I'm fixing an arbitrary P and an arbitrary R and taking Q to be P power R. The first statement is there exists a field of order Q. Second statement is that any two fields of order Q are isomorphic, which we'll prove. Third statement is that if you take a field of order Q and take the multiplicative group of non-zero elements, certainly it will be a multiplicative group of order Q minus 1, but it is in fact a cyclic group. Okay, so that's the third statement, which remember I illustrated here. Here alpha generates K plus, K cross. So it's a cyclic group. The fourth statement says that if you have a field of order Q, the elements of K are actually roots of this particular polynomial x power Q minus x. Every element satisfies that. And a field of order P power R contains a field of order P power K if and only if K divides R. And finally it tells also that the irreducible factors of this are exactly those irreducible polynomials whose degree divides R. Okay, so this may not seem very clear, but we will prove all these statements. I will actually skip some of the proofs because they involve some group theory and some calculations which I would try to avoid now. I will try to sketch the proof of all of them, but I'll quickly finish the proof and I will focus on examples. One example we have already done, and we want to now prove this. So I want to prove the structure theorem. So remember, in the example that I did before stating the theorem, how did we construct a degree 4 order 4 field extension? Order 4 field, we started with order 2 field, found a polynomial of degree 2 which is irreducible and went modulo it. So now you can see how to construct a field of order 8. All you need to find is a degree 3 polynomial which is irreducible, go modulo that. In general, if you want to construct a field of order 5 power 5, what you do is start with f5 which is z mod 5z, find a polynomial of order degree 5 which is irreducible and go modulo it. Only problem with this approach is that it becomes tricky to exhibit such irreducible polynomial, and it's actually not easy. How do you know that there is such an irreducible polynomial and then go modulo that? So we will take a different approach, and this is an indirect but easier approach to show the existence. So I will not prove this in the order in which I wrote. I wrote in that order because this is the sequence that you should remember, but we will prove it in a different order. So we will prove D first. So I will prove all of these one by one. So let's prove D. So what is D? D says that if you have a field of order Q, elements are the roots of this. So this is very easy. So let K be a field of order Q. So remember, always we'll keep this in mind. So I'll put it in red. Always Q is equal to P power R, P prime R at least 1. Okay, so this is the notation. Q stands for that. So let K be a field of order Q. We'll prove later that such a field in fact exists. Let K be a field of order Q. Then K cross, let's say, is the non-zero elements of K. Right, so this is a group. So by definition of a field, is a group under multiplication. K cross is a group under multiplication. Right? Every non-zero element has an inverse. So it becomes a group under multiplication and its order is q minus 1. Because k has q elements, you remove 0, so it has q minus 1 elements. So it's a multiplicative group of order k minus 1, q minus 1. So if alpha belongs to k cross, then by Lagrange's theorem, alpha power q minus 1 is 1. Right? If you have a group of order 100, every element has order dividing 100. So that means that element power 100 is identity element. So alpha power q minus 1 equal to 1. So now if you multiply both sides by alpha, you get alpha power q equals alpha. Right? Multiply by alpha. I am taking this equation and multiplying by alpha both sides. Alpha power q minus 1 becomes alpha q and 1 becomes alpha. So that means every element of k cross satisfies this. Certainly 0 satisfies this. Right? So now that means every element of k this is relation. So every element of k is a root of x power q minus x as required. Right? So this is very simple. So remember, what did I say in D? I said every element of k is a root of x power q minus x, which is of course a polynomial in Fp. Remember, because the coefficients are 1 and minus 1, which are in Fp. So this is true. So D is done. So what I am going to now do is C. In fact, I will not prove C. So we will skip the proof of C. C says that the non-zero elements of K, which form a multiplicative group of order q minus 1, in fact is a cyclic group. This is an important statement that we will use later, but we will skip this. It uses some facts. So this is really a group theory statement. It uses some facts from group theory. One way that you can prove this is using something called the structure theorem for finite abelian groups. So it takes me away from what I want to do, and I don't want to spend time on that. So I will skip the proof. You can read this proof in any book. For example, Art in Algebra is what I am using, where he proves this. So you can read the proof. It's not a difficult proof at all, but it uses some group theory which I want to avoid. So we will skip the proof of C, which is that every the multiplicative group of non-zero elements of K is a cyclic group of order q minus 1. So let me stop this video here. In the next video, we will continue the proof and finish the proof and then do some examples. Thank you.